Good early morning. This is my English speaking practice. And I solve problems on LeetCode. And today I'm going to solve this problem. Let's get started. Given two integers n and k, return all possible combinations of k numbers chosen from the range 1 to n. You may return the answer in any order. So here's the example. If n is 4 and k is 2, we have to pick 2 from 1 to n. So the output is like this. And we don't care about the order, so 1, 2 or 2, 1 is fine. Either is fine. Okay, that's simple. So let me try. Yeah, so I have to check all combinations. So yeah, we have to decide if we choose the number or not choose. So I think the backtrack is a good way to find combinations. But I'm not good at backtrack. But yeah, I learned before, so I believe I can do it. And there are n and k, and backtrack is here, and so basically backtrack function takes remaining. So if remaining is 0, we finish backtracking, and the current list of integers is the one of the answer. So we declare the array to hold results, and we append the current list to the answer array, and return finish the backtracking. Right? And if the remaining is more than 0, we update the current list. Yeah. Yeah, we have to Mm, so the candidates is like this. List. What? List. And we are basically we are looking at the number from the start, a smaller one. So yeah, we should take the current index or something like that. One, two, three, 1, 2, 3. So in this case, the candidates are 1, 2, 3, 4, and for the first loop, we can choose the 1 or 2 or 3. So we have to implement this logic. So there is a candidates, and we should narrow the candidates of this loop. So I mean, for the first loop, for example, for the first loop, remainings are 2, because we have to add 2 numbers to the current list. So we shouldn't go through the 4, because if we use the 4 as the first element, we cannot append next, right? So we have to implement this logic. So here we update the remaining. Yeah, and in this case the remaining is 1. So let me try the First, the idea that comes to mind first. Yeah, this is the idea. If the remaining is 2, we have to take the 2 elements from the last. So we calculate, we apply the negative signatures, and the until is the until means the pointer to go through. So in this case, since we apply the negative signature, so we point it from the end. So if the remaining is 2, -1 and -2, so the until point here, between 2 and 3, so this loop go until 2. Okay. So we choose 1 or 2, and we do a backtrack. So basic idea is like this. For the first loop, we append the 1 and backtrack. So go to next stage. And in this case, the remaining is gonna be 1, so the next loop can pick 1 from 2 and 3 because the until point points here. And the first loop will choose the 2 and call the next backtrack function, and the remaining gonna be 1. And at this point the remaining gonna be 0, and so the pointer points here, so we can choose 1 from 3 or 4, and for the first loop we choose 3, and the remaining is 0, so we can append the answer 1, 2, 3. That works. So like this. Hmm. Oh, maybe we have to copy the array as the answer. Um, until it's -1, -1. Mm-hmm. Oh. Oh, I see. If mm, the until might be 0. In this case, if I use this syntax, it means the before 0, so that is an empty list, right? So this works when the until is less than 0, because this is, yeah, the minus means negative number means it points from the end. But if the until is 0, we have to it means it equals to the entire list. So how about this? Okay. And I also have to decide the start index, because we have a duplicate. We use the duplicate numbers, so and the C is the number itself behave as the index, so we can use the C here. If the number is 1, the index is 0, but the next index should be 1. So we can use C. One, two, three, 4. Yes. So I see. Yes. Looks good, so submit it. Nice. Good. And okay, let's add comments. We prepare the array to hold the result. And we generate the candidates numbers with n. and we use backtracking because this is a problem about combinations. So yeah, we are going with pick one, and then and after exploring, we pop it and go to next. The remaining means the number we should append to the array. The current means the current list of integers we are building now, and the start is the index where we should start the loop. If the remaining is 0, the current list is the answer, so we append it. Otherwise, we decrement the remaining since we append the one number below. And here we going to decide the end of the index for loop. Yeah, we have to save some elements for the future loop. So the end of index, yeah. So the end index is based on the remaining. Here, this is just a little bit tricky. Yeah, the until might be 0. So we switch the way to decide the end index. Yeah. We pick one. And call the next backtrack functions. Oh. So first we need a place to store all the results, and here we just make our candidate numbers from 1 to n. Now we are gonna use backtracking. The idea is we pick one number, explore what happens, then we backtrack, basically remove it and try the next one. Remaining is how many more numbers we still need to pick. And current is the list we are building right now, and start tells us where in the candidates we should start looping. Okay, if we don't need to pick any more numbers, that means current is the full combination, so we save it. Otherwise we still need to pick something, so we decrease remaining because we are about to pick one. For example, if candidates are 1, 2, 3, 4, we are just deciding where to stop our loop. The reason is we need to leave enough numbers for later picks. We need to leave enough numbers for later picks. And yeah, this is a little tricky. If until it's 0, the slicing works differently, so we just handle that case here. So here we pick one number, then then call backtrack again with one less to pick, and finally we pop it out to backtrack. Yeah, good phrases. We need a place to store all the results. We just make our candidate numbers from 1 to n. Now we're gonna use backtracking. The idea is we pick one number, explore what happens. And current is the list we are building right now, and start tells us tells us where in the candidates we should start looping. Where in the candidates we should start looping. Yep. If we don't need to pick pick any more numbers, that means current is a full combination, so we save it. Otherwise, we still need to pick something, so degrees remaining because we are about to pick one. For example, if candidates are and we are deciding where to stop. We are just deciding where to stop our loop. We need to leave. This is nice. We need to leave enough numbers for later picks. There is a lot of unnatural part. Candidates candidate number up to n, because we are solving a combinations problem. How many numbers we still wish to? Okay, but this time I use speech to text, so that's why, yeah, that's why this is not good. Yeah. That's why these comments are worse than usual. Okay. Let's go to next. '80. Remove duplicates from sorted array 2. Okay. Given an integer array num sorted in non-descending order, remove some duplicates in place, such that each unique element appears at most twice. The relative order of the elements should be kept the same, since it is impossible to change the length of array in some languages. You must instead have the result be placed in the first part of the array nums. More formally, if there are k elements after removing the duplicates, then the first k elements of nums should hold the final result. It does not matter what you leave beyond the first k elements. Return k after placing the final result in the first k slots of num. Do not allocate extra space for another array. You must do this by modifying the input array in place with of one extra memory. Okay. Anyway, create files. Remove duplicates, but we have to keep it twice, so how about use 2 pointers? The one is the index where we should write, and the another one in this indicates where we are looking which is the correct. Yeah, where we are looking. So yeah, we cannot allocate extra memory, so yeah, we have to solve this with a constant extra space. So we have 2 pointers. The left one is, yeah, it start at 0, and the right one is also start at 0. Yeah, left one means the where we should write, and the right one means where we are looking. And yeah, okay, this start with 0 because -2 because basically we have to advance the pointer by 2, right? But okay, in this okay, there is a case where the element is only 1, so this idea is not good. -1, and when the loop starts, we assume the updating is finished in the previous loop, so basically we have to increment the writing pointer. Writing and looking. We update the since we and looking means looking points here at first, and if the next yeah looking here and looking at here. If it is same, we advance the pointer forward. And if it's not same, the looking pointer points here at where it means at the end of at the last index of the duplicates, right? And also I want to count it. And if the count is more 2 or more, we write twice. Okay, we can yeah, this is better. And and this pointer points the last index. So finally we have to increment the looking pointer. And 1, 2, 3, 4, 5. Yeah, we have to return the k. So that means writing index. I see. Yeah, that's good. submit it. Okay, nice. Yeah, we use 2 pointers since we cannot allocate the we cannot use we can use only extra constant space, and we are gonna look at the end of the list. Yeah, and we count the appearance of same number. So we advance the looking pointer as long as the numbers are same. Yeah, here we remove the duplicates. Yeah, remove the duplicates. We are allowed to write the number twice at the most. So if otherwise oh, getting better. We use 2 pointers since we can only use constant extra space. We keep scanning until we reach the end of the list. Scanning, not look at. or iterate until the end of the list. Okay, so the scanning is good. Getting easier to understand. Getting readable. We count the appearance. We count how many times the same number appears. Yeah, I should use more how many. Yeah, how many times, how many characters. All the same. We advance the scanning pointer while the numbers are the same. The same. Okay. Can I go to next? Oops. Yes. There is an integer array num sorted in non-descending order, not necessarily with distinct values. Before being passed to your function, nums is rotated at an unknown for bit index k, such that the resulting array is like this, 0 indexed, and for example, 0, 1, 2, 4, 4, 4, 5, 6, 6, 7 might be rotated at pivot 5 index. Pivot index 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So but it should start with k. 0, 1, 2, 3, 4, 5. Ah, yeah, the 5 is here, so the array becomes 4, 5, 6, 6, 7, 0, 1, 2, 4, 4. Right. Given the array nums after the rotation and integer target, return true if target is in nums or false is in nums. Yeah. Mm. How to solve this? Yeah, I want to use binary search. It might work. It might work. But yeah, there is yeah, there are several cases to handle. Else, if target less than nums number at the middle, um, the target is less than the let's look at the left half. Look at left half. So the right pointer is middle -1, and otherwise how is this case? The target is less than middle. Yeah, target is less than the middle, but the target is also less than the left. So for example, the target is 1 and the middle points at point 8. Yeah, so the 1 is less than 8 and also less than 2, so we have to look at the right side. So we have to update the left pointer like this, because the target might be in the right half. And the target is greater than number at the middle. So we check like this. So in this case, the target might be in the right half, so we update the left pointer and vice versa. But in this case, we have duplicates. We have the duplicate elements. How do they affect? Hmm. I'm not sure. This problem is similar to search in rotated sorted array, but nums may contain duplicates. Would this affect the runtime complexity? How and why? So maybe we can solve this problem with this code, but I have to answer the follow-up questions. Yeah. I'm not sure how the duplicate elements affect the runtime complexity. Cause as an example, let's think about this case, and we want to find the target is 1, and we first, the middle is like this here, and the target is greater than the middle, so first we look at the right half, but this point is less than the target, so we update the right pointer here and we search for the left half. Alright, and the middle is like this, and this is 0, so we are going to search for right half, and here, and search for right half and here, and we can find it and return it. Yeah, it doesn't affect. This is a very simple binary search. How about this case? We want to find -1 and the target is less than the middle, so we search for left. Yeah. What? Is this wrong? Target is less than the middle, so we reach here. And the number at the left is greater than the target. So we update the left pointer. That means we search for right. Oh, this is not correct. Is this a valid rotated sorted array? So yeah. Yeah, this is buried sorted array, and compare at first. This condition is not good. I'm confused. So in this case, there is no they are normal arrays in ascending order. I gave up. Wow. Low. Hmm. This is simple. Yeah, this is simple and vice versa. Uh, the difference is here. We have to take it consideration. Yeah, if they are the same, we just increment the left pointer. I feel like I understand. Yeah. The beauty of this solution lies in its adaptability. While binary search is a straightforward algorithm on solid arrays, this problem added the twist of a rotated array and duplicates. By understanding the structure of rotated array and handling duplicates wisely, we can still achieve efficient search performance. To tackle this challenge, we employ a binary search strategy taking into account the rotation and potential duplicates. The primary goal is to identify the solid part of the array in each step and narrow down an or search based on the target. Our approach doesn't involve searching for the rotation point. Instead, we modify the binary search to work directly with the rotated array. If the value at the low is the same as the value at the mid, we might be dealing with duplicates. In this case, we increment low to skip potential duplicates. If the left part of our interval is sorted, we check if our target lies within the sorted intervals. If it does, make sense. So here we have to care about we have to care about duplicates. In this case, normal. Yeah, normal case. This is the normal case, and the target is in the left half. Yep. Otherwise, I can understand this problem. If left, so in the rotated sorted arrays, we have one sorted side, left or right. Okay, so we have to find which side is sorted like this, but there is a duplicate additionally, so yeah, in this case we cannot decide which side is sorted, so in this case we have to move left forward by one. Okay, that makes sense. That makes sense. And so since we add this process, the time complexity would be O of n, because in the worst case we have to scan one by one with this code. Okay, I will go finish.